work, what I am going to present is a very brief. We really didn't get time to write an elaborate paper. And this work is an offshoot of the project we have completed in first phase for Bhel, Hyderabad. They are pulverizing group actually. Crucial issue in desulfurization is limestone, because that is easily available as raw material, and typically high quality limestone is available. And that limestone in pulverized form reacts with sulfur dioxide. So that is the standard practice throughout the whole world, followed for every coal utilities. That means desulfurization with the help of pulverized limestone. So very crucial is how do you grind, how do you pulverize that limestone, because entire efficiency of the process depends on the desired fineness. This word is very important, desired fineness of limestone. Desired in the sense its size must be such that large surfaces of particles are available for reactions. Large surface areas. You can get large surface area only when you have very fine size particles. More the number of particles, larger is the surface area. But grinding or pulverizing is a very expensive operation. So if you overgrind, that means if you go for almost infinite fineness, that immediately escalates the cost. So the challenge basically is to produce a very specified, narrow size range pulverized limestone. And question is, how do we do that? Because FGD was not required in India, so Bhel did not have FGD technology initially. That is the reason why Bhel approached us, and we took up this work. Before I move on to the main question, this first slide I have put to show the paradox. To show the paradox in the sense that FGD is practiced as a pollution control measure to reduce drastically the sulfur emission. All right. But limestone grinding alone for cement manufacture is a major polluting industry. And carbon emission is very significant. You can look at this figure for 3 different plants, 2 different types of methods followed. One is Portland cement, that is, and another Portland limestone cement. I mean, there is a blend. So cement blended with limestone has economic and environmental advantages due to reduced energy consumption and lower greenhouse gas emissions. Grinding and kiln both contribute to CO2 emission. So the objective is reduction of sulfur emission by grinding limestone and then getting it reacted with SO2. But in that course, we keep on doing carbon emission. Not only the mere grinding process, which consumes a lot of energy, but also you will see the materials we use in the construction of grinding mills and in operating the grinding system. These are all very carbon intensive. So this dichotomy remains and perhaps will always remain in whatever we do for environmental protection. For example, we keep on talking wind power as green power, but we never do the calculation of electricity and steel consumed in the production of those windmill towers or the blades, even solar panels. So if we do that kind of calculation and comparison, perhaps we will see the real reduction in emission through solar and wind is significantly less than what it is projected. Now, removal of SO2 from flue gas, I am coming to the main. Through chemical reaction with limestone depends on quality of limestone, mass transfer and chemical reaction rate in water slurry of limestone and SO2 gas. As pure as possible limestone is required. That reduces the cost. That improves the efficiency of the system. And we have a very large reserves of that kind of high quality limestone in Madhya Pradesh, in the area many of you perhaps know, Satna, Katni, Maihar. That is the reason we have a very large number of cement plants there. So after Jabalpur, if you move towards Bombay by that route, Allahabad-Bombay route, after Jabalpur, one after another, this cement producing belt, limestone producing belt will come. And we have huge reserves. Almost lying, very typical is the mining pattern, very typical is the deposit pattern. Almost like childhood slates, I don't know how many of you have used, but I did use in my childhood. Almost like slates, flats virtually, and very large slabs, not horizontal, inclined layer after layer, and reasonably soft and reasonably pure. Temperature of slurry, stoichiometric ratio, particle size and surface area of limestone also play important roles. It is important to grind limestone to desired fineness and at low energy consumption. Desired fineness means generally the limestone from mine what we get after initial crushing, ideally it should be 1 inch size, 25 mm, less than 1 inch, 25 mm. But very frequently that does not happen because limestone procured or to be procured for FGD system from the mines are not big mines. They are not big operators. They are mostly small operators, small deposits. So they do not have very sophisticated crushing system. As a result, very commonly we get up to 75 millimeter, sometimes even 100 millimeter size limestone pieces. We call it run-of-mine limestone as it comes out from the mine. And that limestone has to be reduced to a size of 90% passing, 90% of the mass passing 40 to 45 micron. All right. So this is a huge, we call it reduction ratio from 75 millimeter to 0.045 millimeter. Now while we do that, it is desirable that percentage mass of less than 10 to 15 micron will be minimum. That means for desulfurization purpose, limestone particle size what we require is broadly in the range of 15 to 40 to 45 micron. But it is not possible to grind or pulverize exactly on the basis of such a narrow size range. Crushing, and you have seen crushers in your power plants, you have seen pulverizers in your power plant mills. They do operate on the basis of a targeted top size. That means top size of the particle will be, say, 75 mesh. 200 mesh. That is 75 micron. For crusher, top size of the crushed coal particles, let us say 20 mm or 25 mm. We do not specify the lower size limit because this is not possible. Because when you crushing or pulverizing or any breakage actually produces a distribution of sizes, not 1, 2, 3, 4, any kind of limited number of or certain specified number of sizes. That is the challenge. The grinding of the clinker is generally done by blending both the classes of materials or separately ground and then mixed. This is true for cement making. Abroad, there are places, there are power plants. Why I am making this point is abroad there are power plants where FGD plant, limestone supply comes from different sources. So there are many instances where they are blended and they are pulverized. But by and large in India, most probably that is not going to happen because Satna, Maihar, Katni, this is the most dependable region and we have huge reserves of limestone. If it happens, what is important is to note what is the grindability of more than one source of limestone if you are using. If grindability is similar or very close, then they can be blended and pulverized. But if grindability is different, they have to be pulverized or ground separately and later blended. Oh. This is a classical desulfurization system. It can be carried out using dry limestone powder, semi-solid liquid, and in slurry of limestone. Among these, the limestone slurry gives the highest efficiency. And the reason behind their individual efficiencies lies on mass transfer mechanism of SO2 gas on limestone surface. So again, question of surface comes back. And you can see this is a very schematic, typical diagram of how desulfurization is done using limestone. This is a typical composition of limestone. When we say limestone, what do we mean? What do we have in it? Calcium oxide 49.9 to 54.5%, typical range. It can be little less, it can be little more. Then we have magnesium oxide, we have silica, we have Fe2O3, lesser we have Fe2O3, better it is. These are around impurities. Silica can be present as sand grains. Silica can be present as clay, which is there as impurity. Clay is an integral part of any soil. Anything you take out, unless and until it is a deep underground mine, anything you take out from surface or close to the surface, be it coal, be it iron ore, bauxite, limestone, anything. Clay will be there. Question is, what is the level of clay content? So silica can be present as individual silica, sand grain, silica alone. Silica can be present as part of clay. Alumina is another component of clay. Iron impurities are not desirable, but iron impurities, this level of iron impurities are again very common in soil. And then we have significant loss on ignition. Now, various reactions and physical steps for the process when we do this desulfurization are as follows. Diffusion of SO2 through the gas film near the gas liquid interface. Diffusion of SO2 in the liquid phase. Dissolution of SO2 on water phase and reaction with calcium carbonate. Also in parallel, dissolution of calcium carbonate in water. 3 and 4 must go almost parallelly at par. And reaction between SO2 and CaCO3. Loss on ignition. If you heat, if there is presence of carbon bearing material, they escape. This is what we call loss on ignition. So very generalized reaction, actual reaction is very complex, and it is very difficult to get the process defined in terms of one single reaction. The reason is, look at the table, so many mineral constituents are present. You have iron, you have alumina, you have silica, and they are in different forms. When I say clay, this Al2O3 and SiO2 I am showing as separate, but they need not be separate. They can be in the form of silicate. So, actual reaction is extremely complex, but the main reaction which we are interested with, in a very generalized way, we can write like that. All the aspects of mass transfer for solid liquid gas diffusion as well as chemical reactions are involved in desulfurization. Limestone corresponds to calcium carbonate with molecular weight 100, which during heating decomposes to calcium oxide 56 and CO2 44. During removal of SO2 from flue gas, apart from calcium oxide, other alkali compounds like MgO, sodium oxide, potassium oxide, etc. also take part in reaction. Sodium oxide, potassium oxide, they are present in clay. Whatever be the clay, whatever be the minute amount, which sometimes become at the level of ppm, but they will be there and they take part in reaction. I will take a sip. All such compounds react based on their affinity to CO2, reaction rate constant, stability of formed carbonate salt, temperature of slurry or mixture, etc. The particle size distribution of limestone received from the grinding circuit also controls the absorption process, that is reactivity. To a major extent, due to a change in the exposed surface areas as a function of different particle sizes and the particle size distribution. This is very important. Hence, optimum grinding is required. If you do not have optimum grinding, your FGD will fail or FGD will perform below par. Very similar. if your mill does not perform, you will lose unburnt carbon in fly ash. You cannot burn coarse particles. These are two very crucial equipment in the grinding circuit. Where is that? This is the mill inside. Feed end, discharge end. Horizontal installation, basically cylindrical shape. And it rotates at certain RPM. Ball mill discharge streams, this is overflow type. That means material gets discharged as the overflow through the other end. There is no mechanism to push it out, but because of the continuous entry of fresh feed or new feed, the material keeps on moving towards the other end. Completely wet system, though dry grinding is done, but dry grinding is very expensive. And unless there is a very specific requirement for dryness of end product, we don't do dry grinding. Mill discharge goes to the other unit, what is shown at the top. This is called trommel. Trommel is a fixed, or it can also rotating screen. Again cylindrical, you can see. And this part, what you see, or inside here, this is very fine mesh. So the mill discharges to the trommel, which is fitted at the other end, discharge end. All the ground particles, they pass through the mesh. That is the measure, one control point, that yes, particles have been reduced to the desired size. Balls sometimes get discharged, sometimes damaged balls, we get damaged balls because it continuously rotates, so balls move up and drop, move up and drop, move up and drop. Usually from feed end to discharge end, 5 to 7 drops, 4 to 7 drops, 5, 6. Upward movement drops, like that. So sometimes balls get damaged and they get discharged. Sometimes balls no damage but still get discharged. Sometimes very unexpected, some alien material from any previous operation, they also come along with, or from mines. So purpose of trommel is to arrest all these, not to allow those things to move into the subsequent phase of the circuit. And at the same time, to have a control over the particle size produced. That's why trommel is very important in limestone grinding. In metalliferous ore processing, when we do lead, zinc, copper, very rarely we go for trommel. Because prior to milling, there had been many stages of other operation. Whereas here, this is basically the first stage. Maybe prior to it, there is a crusher, one crusher. So one should not take a risk. Oh, This is the trommel. Yes, at the outlet. This is the trommel what I had shown in the previous slide. All right. No. Through the perforation here on the base, you can say, or whatever, bottom portion. No. This whole body is perforated within a steel frame. Whole body. Yes. Through the percolation it goes here, sump. Because rejection is very little, so we have not shown separately a reject flow. That is the only reason. Okay. So this is the main slurry which after getting discharged from mill, passing through the trommel, going to the sump. From sump it is pumped to hydrocyclone. This is the last unit. Hydrocyclone is a size classifier, particle size classifier. You are familiar with screens. Screens are used for coarser material. And usually for particle sizes less than 0.5 mm, 0.4 millimeter, hydrocyclones are used. And we say that if open area on screen surface is 20% or less open area, then screening becomes uneconomic. We have to look for size classifier either on the basis of gravity settling or on the basis of hydrocyclone. So there is another group for which is called mechanical classifier. Whereas hydrocyclone is on the basis of centrifugal separation. So hydrocyclone overflow, this is what we call overflow. Hydrocyclone overflow is the final limestone slurry which is going for reaction with SO2. Whatever are coarser particles, they from through hydrocyclone underflow, it is fed back to ball mill again. So in ball mill, you actually have here by conveyor belt, you are having fresh feed. And this is your what we call recirculating load. That means total feed to ball mill consists of fresh feed and recirculating load. Recirculating load can be up to 100, in case of limestone, it can be 150 to 200%, even little more. Because limestone is soft. If the material is hard, for example, iron ore, it can be 300%, 350%. Even there are instances of 400%. No material gets pulverized in one single pass. No material. So they have to come back. Now, my purpose of elaborating to that extent is, when you procure for your plant FGD system, these are the things you should be keeping in mind about the main units. Next, what is important, what again you should insist with the vendors, is the control system. Modern grinding circuit consists of fully 2-3 at least controllers. 3 things we can definitely and easily control, and we should do it. One is feed rate controller, because that controls the pulp density. That means concentration of solids in slurry. That is what we call pulp. So every grinding mill operates on the basis of a specified pulp density. Pulp density is very important. Why? Because larger the concentration, more is the coating of particles on the surface of the balls. More is the coating on the liners inside the mill. More coating, more grinding. Less coating, much more wear and tear, because more and more iron to iron, cast iron to cast iron contact. So reduced life of mill, reduced life of all its pairs, reduced life of balls, faster de-shaping of the balls. So very important is pulp density control through feed rate control and water flow control. Both are required. Next important is pH control. You should be very clear that it is ambient. There is no chance that it should be left for even little bit being acidic. It must be strongly ambient. So pH control you can do here itself, or you can do separately for the water, because you are using already in power plant a huge water supply system and recovery system. So there also you can do. But one thing to be clear is that water supplied to FGD system for grinding purpose has neutral pH. Sorry, not ambient, neutral pH. Finally, in almost all advanced countries and all major technology providers, what do they use? What I have shown here as PSI, particle size analyzer. It is expensive. It may not work out for small plants, but for high megawatt plants, large megawatt plants, it can be covered. Cost, their capacity can cover the cost. This is online particle size analyzer. So there are different models available, there are different methods available now. So what is the size distribution of the particles which are finally going for limestone, for reaction with SO2? That means, am I grinding to my required targeted size and size distribution, or I am deviating from that? Because it is a highly ancillary unit, PSI, we have not suggested PSI to be clubbed with control system, because then much more control would be required. Expenditure would go up. And PSI data you can use as on-off control, that you stop the system. You check your mill interior, you check your cyclone pressure. I am coming to that. So usually nowadays for all large, because abroad we don't have small megawatt plants, it is all large megawatt plants. So almost everywhere it is with control. Did I miss anything? Okay. Pulp density, feed rate control to ball mill, pulp density inside mill, pulp density of cyclone feed sump. Not only pulp density, also level. Level is very important in the sump. The problem with level is, if level is low, then immediately particles will have a tendency to settle. Feed pressure to cyclone, level of slurry in mill discharge sump. All this should be controlled. No compromise on that. Modern plants use advanced control tools or expert system based on AI, and PSA, as I told, is one of the important instruments that is used everywhere on continuous basis and for controlling the fresh feed rate to mill. Benefit of using advanced control tools: it increases process stability and performance, enables more utilization of the process through increased equipment availability, uses an open and easy to learn system with process visualization, connects to all existing plant control systems. This is true for general limestone grinding system that connects to all existing plant control system, but this may not be true for FGD system limestone grinding, because this is a very exclusive in nature. Minimum size is, as I told, 90% must be 40 to 45 micron. For example, if you are using limestone in some of the I get your point. Weightability has to be determined. Weightability has to be, because this is a basic property. So there are few, I will come to that. Okay, please remind me if I miss, I will come to that. Basically, at the end, I will tell what tests are essential. Am I crossing time? Right. Economic aspects of grinding. Grinding circuit involves very large capital investment and the process is energy intensive. You need very strong structurals to install a grinding mill. You know yourself already because of your coal mills. Grinding at low investment and reduced energy consumption cost at desired granulometry is the real challenge. Design and selection of the main grinding equipment for a plant remains empirical to a significant degree. There are equations, but these are all empirical and depends mainly on designer's ability. Basic equation is for power calculation when it comes to grinding mill selection, that from this size to this size, what will be the power consumption depending on hardness of the material. Hardness is defined in terms of bond work index, BWI. This is one primary test we have to do, bond work index. Next is abrasion index. How abrasive is the material? Number 3, weightability of limestone. That has to be determined. Number 4, chemical analysis of limestone. These 4 tests are essential. For grinding mill sizing and hydrocyclone, for full grinding circuit design, bond work index and abrasion test. And for selecting right kind of limestone, required is absorption test and complete chemical analysis. All right. Surface area requirement you can calculate from size distribution, because at that size we assume that all particles are round in shape. Particle shape affects as the particle size keeps on increasing, and particle shape effect is less and continues to be lesser as the particle size goes to finer. And then we use correction factors. There is a host of correction factors. So we calculate power and then we use correction factors. Almost, I think, 12 or 13 correction factors are there. Finally, we get a final value of horsepower, say 900 horsepower. So we visit the websites of the vendors or manufacturers, and we first look for matching horsepower of the mills produced by them. If that matches, then that is our primary selection. Then again we come back, we do some recalculation, then that is the point when we start negotiating with the vendor. Then little bit adjustment here and there, vendor has to agree, they agree. If I find 900 horsepower is not manufactured by anybody but 450, then we will go for 2. 450 into 2 units. So horsepower is the most important thing. And not limestone grinding, but as a general figure, let me tell you that in the United States, 68% of the power consumed in the mineral processing plants, whole country, is consumed in grinding alone. Grinding is so power intensive. 68. Another 8% goes in crushing. So 68 plus 8, 76. That means hardly 25% is consumed in everything else. So grinding and crushing, the moment question of breakage comes, immediately power consumption will come. Okay. Material specific mill selection considering other physical properties along with bond work index may reduce the cost of grinding. Analysis of the performance of installed machines in actual plant is important aspect to improve the productivity and reduce the cost of grinding. Like in your neighboring plant or some plant, what kind of liners they have got? What is the material of construction of that liner? What is the steel composition? What is the cast iron ball BHN? Hardness number. These are very interesting, small things, but very important things. Approach based on genetic algorithm and simulation models to evaluate the optimum operating parameter levels can be helpful. Once you start operating the limestone grinding circuit, try to generate some initial data, and that data will later help you in creating your own simulation model. Very simple simulation model on the basis of which you can improve your own limestone existing grinding circuit performance. You have to do a bit of calibration, that pulp density range from say 35 to 45% solids. Right? pH of water strictly 7, no variation. Level usually in some beans, bunkers, we specify level in terms of H. H we take as the complete depth or height, inside height of the bean, bunker or sump. Alright. Then we calibrate. What is my targeted upper level? 0.9 H. That means up to 90% of that height I will get filled. Or 0.8 H. What is the lower level? 0.3 H, 0.4 H. So this kind of calibration you have to do. Once you do, a typical, very common, very simple simulation model you can get for your limestone grinding circuit. Because there are only effectively 2 units. hydrocyclone and ball mill, nothing else. Hydrocyclone selection is also empirical. There are empirical equations. Time is up now. It is also standard textbooks are there where you get both. Of course, textbooks have limitations. You have to work more on that. Anyway, I think I have already taken a lot of time. I think this is the last slide. Proper grinding of limestone is important as it governs the overall economics of limestone processing for FGD system, along with governing the quality of SO2 removal from flue gas. Grinding circuit design and control using advanced tools is needed to optimize good quality limestone. Reliable information about chemical reaction between limestone slurry and SO2 is important. Real challenge is getting 90% passing through 40-45 micron with minimum percentage of 10 to 15 micron. Okay, thank you.